or you could have divided everything in that fraction by the single largest term, would have been another way to get the answer, or you could have used your horizontal asymptote rules. Lots of different ways to answer those limits as x is going towards infinity, but eventually L'Hopital's rule is going to be the easiest way. All right, anyways, factor and reduce had the first one, limit to infinity, so we found the biggest terms, worked with those. That was the second example. Now we're going to do the third one, which is going to be using the conjugate trick. So let's go through. If I were to plug it in, let's see, limit as x is approaching 7. 7 plus 2 would be 9. Square root of 9 would be 3. 3 minus 3 is 0, so I'd get a 0 on the top. 7 minus 7, 0 on the bottom. So I do get one of those indeterminate forms. How very lovely. That means I don't know what the answer is right away. There's going to be an answer, I just don't know what it is. I need to do something, and that something, whenever you saw a radical and then either a plus or minus a number, that strategy was to utilize the conjugate. So I'm going to take this original expression and I'm going to multiply it by a very strange looking 1. I'm going to multiply it by the conjugate of that radical term. So I have the square root x plus 2 plus 3 on the top, and then I got to do the same thing on the bottom, square root of x plus 2 plus 3. So I'm using the conjugate of the radical term. Now, if you remember, here I've got two layers. On the top, I have the conjugates, and on the bottom, I have non-conjugates. The two things that are not conjugates, you want to leave them factored. Don't multiply them out. You're eventually looking for something to reduce and to simplify. So if you distribute all this stuff, you're just going to have to refactor it anyways. That's silly. Don't do it. That's a waste of time. So leave the non-conjugates factored. Hopefully you remember how annoying I was trying to remind you about all that stuff way back when first semester. So I'm just going to copy this denominator, leaving the non-conjugates factored. But the two things that are conjugates, which in this case happen to be in the top in the numerator, those things you do multiply out. So again, top, bottom, that doesn't matter. If the two things are conjugates, you multiply them out. If the two things are not conjugates, you're going to leave them factored, right? So here, let's multiply. If I have the square root of x plus 2 times the square root of x plus 2, well, that's just going to give me x plus 2. Then when I multiply it, I have 3 roots of x plus 2. And then I would have a negative 3 roots of x plus 2. Remember, when you multiply out conjugates, the middle two terms are always going to cancel. That's why we really like conjugates. So here, when I FOIL them out, the first times the first gives me this chunk, then the outside plus 3 roots, then minus 3 roots from the inside, those are going to cancel. But then I have the last times the last, positive 3 times negative 3 would be a negative 9. So I left the non-conjugates, which were in the bottom, left them factored, and then I actually multiplied out the conjugate. Now here I go, I'm trying to still see if something will reduce, because I've got to eventually plug in the 7, but if I do it right now, I'm still going to get a problem. However, x plus 2 minus 9, all of that plus 2 minus 9, that's the same thing as x minus 7. So it doesn't initially look like it's going to match, but once you then combine the like terms, the positive 2 and the minus 9, you'll see that you will have some stuff that reduces, and then I'll have this limit. As x is going to 7, you have 1 on the top, and then all that's left over in the bottom is this bottom right chunk, the conjugate of that original radical term. So I had to use the conjugate, multiply out the conjugates, then I left the non-conjugates factored, then something reduced, that was really nice, and then after it reduces, you're going to want to go ahead and evaluate it. So let's plug in all the x's as 7. 7 plus 2 would be 9, square root of 9 would be 3, 3 plus 3 would be 6. So we get this answer as 1/6. All right, so that was just 3 examples of all those different algebraic ways. Now, there's lots of other techniques, right? Combining fractions, simplifying fractions. We had a couple of other techniques that we could have done to get around those two indeterminate forms, but those were just some of the big ones. Now, we're going to go through and read this thing called L'Hopital's rule, and it's going to seem a little bit weird at first, but really, once you do it and once you really understand it, it's going to make all these limits a whole lot easier. So let's go for it. It says, not all indeterminate forms can be evaluated by algebraic techniques. Uh-oh, that seems scary. However, another method is used to evaluate them, and that thing is called L'Hopital's rule. Let's read it. It says, if the limit, I have some function f and g, if the limit of f over g, remember as x is approaching 9, if that limit ends up in one of the two nice indeterminate forms, which is a 0 over 0 or infinity over infinity, if my limit results in one of those indeterminate forms, then my original limit, right? Remember, that's the thing that we were trying to get. If I have one of those two things resulting from this original limit, you no longer have to work with the original functions. What you can do is look at the limit of the ratio of those derivatives. So instead of trying to evaluate f over g, what I can do is instead look at f prime over g prime, and then that limit of that ratio is going to be the same thing as the limit of your original function. It's a really weird rule. If you want to kind of delve more into why that rule is the way it is, I can try to link you to a cool YouTube video, but as for now, you kind of just need to know that it will work, right? If this original function gives you one of those two indeterminate forms, hey, take a derivative on the top, take a derivative on the bottom. That's called using L'Hopital's rule, and then see if you can get an answer. All right, let's go back to the first three examples, and let's try to redo them using L'Hopital's rule. Remember, we did factor and reduce, then we had using the biggest terms for the limit to infinity, then we had the conjugate trick for the third one. All that was great, but there's the one calculus rule that covers all of those algebraic strategies. So let's go back, and let's use L'Hopital's rule on those first three examples. Sorry, I have like a very sketchy setup with this camera. I'm trying not to knock everything over and kill myself, but we'll see. All right, remember, this original limit ended up being 0 over 0. It's very important that you always check if one of your, if your original limit is not either 0 over 0 or infinity over infinity. If it's not one of those two indeterminate forms, then you cannot use L'Hopital's rule. You may get an answer, but it's not going to be the correct answer. So always make sure it's one of these two indeterminates first, then you could go through and use L'Hopital's rule. Now notice, L'Hopital's rule is really, really, really nice. You do not have to do quotient rule. You have this function f on the top, you take its derivative, and it stays on the top. You have this other function g on the bottom, you take its derivative, and g prime stays on the bottom. That is not doing quotient rule. It's just doing the derivative on the top, stays on the top. The derivative on the bottom stays on the bottom, and then you're done, right? It's a really nice, really easy rule. No quotient rule. It's easier than that, no quotient rule. Anyways, let's go back up to this first one. We know it is indeterminate, so let's try to apply L'Hopital's rule. The limit would still be the same, so I'd have limit as x is approaching -1. Now remember, that was 0 over 0. It was one of those two nicer indeterminate forms. So now let's apply L'Hopital's rule. I always like to write this little LH. It's a little notation that says, hey, this original function does not work, right? It gave me a 0 over 0, but I'm going to use L'Hopital's rule, after which I will get an answer. The limit stays the same, so I need to take the derivative on the top and then the derivative on the bottom. Let's go for it. The derivative on top, I know it's been a while since you've done any calculus, but hopefully you still know that the derivative of 2x squared, I'm thinking that's just going to be 4x, and the derivative on the bottom, that's just going to be 1. Okay, now let's go through. I've used L'Hopital's rule once. Let's just try to evaluate it. So now I'm going to plug in my x's as -1s. And then look at that. It's the same answer I would have gotten had I done the algebraic way of factoring and reducing, right? The algebraic way works. If you want to factor and reduce, by all means, go for it. But L'Hopital's rule is just a much faster, I think, easier way of getting to the answer. Now, the second example, if you know your horizontal asymptote rules, those are probably easier than doing L'Hopital's rule. But let's say you didn't, and so when you tried to evaluate this limit initially, you got this infinity over infinity issue. You're like, okay, that kind of sucks, but really it doesn't, because you can use L'Hopital's rule. We would still have limit as x is going towards infinity. Let's see, the derivative of 3x squared would be 6x. The constants would go to 0 when you take the derivative anyway, so that's wonderful. The derivative of the bottom would be 4x. That's really awesome. If you want, there's really two ways you could get this answer. You could reduce the x's now, or you could try to reevaluate it. If you tried to plug it in right now, you would still get infinity over infinity, right? Because 6 times infinity would be infinity, 4 times infinity would be infinity. So it's still indeterminate, but you can just take L'Hopital's rule again, right? As long as you keep hitting one of those two nice indeterminate forms, you just keep taking derivatives until one of the layers is a constant, and then you'll get an answer, right? So it didn't work right away. You could have reduced the x's and you would have gotten the answer, but instead, let's apply L'Hopital's rule a second time. I'd still have this limit as x is going towards infinity. The derivative of 6x would be 6. The derivative of 4 would be 4. And the limit of a constant, oh, look at that. It's going to end up being 6/4, which reduces to 3/2, which is the same thing we got when we did it earlier, right? So algebraically, you can do it, or you can use the calculus rule. What's really nice about the calculus rule, L'Hopital's rule, is that it's going to cover all of those different 7 or 8 algebraic ways that we did at the beginning of the year. L'Hopital's rule covers them all. One really easy calculus rule takes care of all those issues. It's really nice. All right, let's go back and let's redo the conjugate example, but instead of using the conjugate, let's go through and use L'Hopital's rule. Remember, I already checked it. It was 0/0. So I can use L'Hopital's rule. Students usually ask, do I have to write this little L''H? Yes, you should probably do something to indicate that I know what I'm doing. I know I'm using L'Hopital's rule. I'm not just changing things willy-nilly, right? I'm using L'Hopital's rule. So it is a good idea to go ahead and write that little LH or write out L'Hopital's rule anytime you apply the rule. It's just a good rule of thumb. Anyways, that one I know was 0/0. Let's take the derivatives, use L'Hopital's rule. All right, it would still be the limit as x is approaching 7. The derivative of the denominator would be 1. That's really easy, going to do that one first. Now here I have the radical. I have square root of x plus 2/3. Just remember, going back to some things, if you have a radical, the derivative is 1 over 2 of the roots. Then whatever's inside would copy inside. If you had to do chain rule, it would go to the top. But here I've got the square root of x plus 2. That derivative would be 1 over 2 roots of x plus 2. Now you don't really need to write over 1. Anything divided by 1 is just itself, so you don't really need it. But I had the top, took its derivative, it stays on the top. I had the bottom, took its derivative, it stays on the bottom. Now let's go through and try to evaluate it. Let's plug it in. I got 7, plug that in for x. 7 plus 2 would be 9. The square root of 9 would be 3. Then 2 times 3. Oh, look at that. It's going to end up being the same 1/6. So factor and reduce using the biggest terms, or if it was a limit to 0, using the smallest terms, or using the conjugate, or any of those other algebraic techniques that we did at the beginning of the year. All of them get covered by the one calculus rule, L'Hopital's rule, which means, hey, just take the derivative on the top, take the derivative on the bottom. That is not quotient rule. It's easier than that. But using L'Hopital's rule, you can get an answer. So those are really nice indeterminate forms. At the beginning of the year, we didn't like them. But now we really do. All right, let's move forward. Let's do a couple more, and then we'll be done. All right.